Hello everyone and welcome to our lecture today. This is our second lecture on software metrics. And as you might recall, last lecture we mainly focused on giving an introduction to software metrics and measurement. And we talked a lot as well about what type of metrics. Do you remember? Nobody remembers? Quantitative, sure. Why don't I just quickly go back? So if you remember, what we did was we talked about that there are three types of metrics. There are, sorry, didn't mean to skip, product, process, and project metrics. And what we spent some time on was we went through the measurement basics, and then we talked a little bit about a framework. And today what I want to do is get into specifics. I guess we didn't really go into a specific category. I think most of the examples that I gave were probably product. But today we're going to focus on product metrics in particular. So that's kind of where I want to put most of our focus. So it's product, process, and project metrics for the person who commented in the channel. So today we're going to talk about product metrics. So just to get started, I'll pause the video, but I want everybody to take 30 seconds, or let's take a minute, and I want you to give some thought to this topic, which is external product metrics. And these are measurements of the software and its environment. And what I'd like you to do is just write down or think in your head about a couple of external metrics that are applied by only observing how the software product runs in its environment or exists in its environment. What are some examples here? And I'll pause and I'll let you take a minute to do this, and then we'll come back and we'll discuss it. So we're back, and what I just asked you to do is take a minute and just think about some external metrics that are related to a software product, meaning metrics that are observed or that are applied only by observing the software product in its environment. So I see a couple things here. One of them is user satisfaction or customer satisfaction. That's something. That's one that was listed. Somebody else listed performance. And someone else listed time to run, defects per lines of code, amount of failures. Someone else said time, I guess performance, resources used. Someone else wrote objective. I'm not sure what was meant there. I'll ask that person to maybe elaborate a little. But okay, we have a few different ones here. Any others that people would like to add? There's no wrong answers. Well, there could be wrong answers, but there's no bad answers. This is about a learning experience, a chance for you to gain some insight. So if you think of something, it's really helpful. Oh, okay. So objective, the goal of the product was achieved. So yeah, so you're talking about like user validation, or you're talking about could be as well number of executions where people are successfully able to complete the task that they start. So if you think about how many people abandon, if it's a how many people actually complete the task versus actually abandon it or something like that, maybe that's something you could think about. Okay, so there's a few, I just jotted down a few myself quickly on the slide before I actually started. So I wrote down failure rate, which I think was one of the things that was mentioned. And I wrote down, which was number of failures per unit of time, right? So the failure rate of the software. This is a little bit different. I think, I'm trying to remember what somebody said. I think somebody made a comment about defects. Am I right on that? Defects per line of code. So not quite that. Defects per line of code would be more a measure of the software. It might not be external. It could be internal, right? Potentially. Because there's lots of ways to find defects. But if you sort of highlight it that you're talking about failure rate when the user's using it, so failure rate out in the wild or after deployment in terms of how many failures per day, per user per day, or something like that, or per 100 users per day or 1,000 users per day. Availability rate is something we often talk about, which is the percentage of time a system is up. This is really critical for e-commerce sites, right? So just think about it as an example, something like Amazon, right? If Amazon goes down for a couple of minutes, how much money does it cost? How much money do they lose? It's probably, I don't have the exact number, but it's not insubstantial. It's definitely, yeah. So the thing is that availability is key for a lot of those systems where there's a large financial implication for going down. Banks, same thing. Availability rates are also really important for safety critical software systems. Think about the 911 system, right? If a 911 computing system or software system goes down and they're not able to deploy ambulances or get calls or whatever, that can impact people's lives. People may die. And so in those systems as well, availability rate, percentage of time the system is up, is key. So defect rate is here, number of defects per size of code. I guess, yeah, I said that could be done internally, but it could be done externally too. So it really just depends on how you're identifying the defects. If you're doing it through testing, then you're typically running the software, so that would probably be fit, as one of the class members said. So let's look at a couple of these in detail, and I'm not gonna look quite yet at these, but I'm gonna look at a couple of other measures. So when we talk about external product, one thing we can think about is reliability. So what does it mean to be reliable? Available means how long it's up, right? Consistent, yeah. So if we go back to that previous slide, that failure rate comment, number of failures per some unit of time, that failure rate is directly related to the reliability of the software, right? Someone meant resistance to failure. It could be resistance to failure, but it could also be just, it's resistance implies it's actively preventing failure or stopping failure. There may not be any resistance to failure. It may just be that failures are infrequent. So reliability, you can think of that as the probability that a system will execute without failure in a given environment over a given period of time. And remember, this is one of those tricky ones because the reliability, let's say we have a software that we use that's used by different clients. The reliability with one client or one company may be different than the reliability with another, or one user may have a different reliability experience than another. And part of that has to do with the fact that programs are used in different ways. Programs are used in different environments. So it's really important here to realize that something like reliability can vary depending on how the software is utilized and where and when it is utilized and by whom, and on what platform. So another thing to keep in mind is that because there's no single number and it can vary, sometimes you can use probability here to model the uncertainty a little bit. And reliability is also time dependent, right? Because it's over a given period of time. So it involves probability, it's over a given period of time, and it's something that can vary a little, which is why we're talking about probability. So let's also go and do a definition of failure, and you'll see why I'm doing this in a second. So what's the definition of failure? So we said reliability is the probability of its given system will execute without failure in a given environment over a given period of time. Well, what do we mean by what is a failure? Well, a formal definition might be any deviation from the specified behavior. That includes a crash. It includes getting the wrong output. It could include getting output late if there's a requirement around how quickly you get it. So there could be a whole bunch of things here. Could be getting too much output, too little output, right? Could it be about, for example, if it would be a failure if you're doing, if you have some sort of video-based software that's supposed to be recording HD quality and it's recording it at a lower resolution, right? You're still getting the video, but it's not the specified behavior. A more engineering view of this might be any deviation from required, specified, or expected behavior, right? What does that mean? Well, required here means by the user, by the environment, sorry. Specified means the same thing as in the formal definition, meaning, what was in the requirements. And expected could be by the user. So if it deviates from what I expect, or it deviates from what the environment requires, or it deviates from what it was specified to do, then that would be an example of a failure. Great. So it's kind of, I'm doing this because we often don't define these things. We talk about failures, errors, bugs, faults, and we don't really say what we mean by these. So this is what I mean when I say a failure. So what about, let's look at some of those other terms, right? Errors, faults, and failures. What do we mean by an error? What's an error? Well, an error can be thought of as a mistake or oversight in the part of a designer or programmer which may cause a fault or a failure, right? So a coding error can lead to a fault or a failure, right? The error is the mistake. It's not the outcome of the mistake, in other words, okay? So the error is actually the mistake that's made by the human in designing or encoding or whatever. This in turn can cause a fault, where a fault is a mistake in the software. So the software does something incorrectly because of an error made by a programmer, designer, or whoever. So an error by somebody in the development team can lead to a fault in the software system, which in turn may lead to a failure when the program is run in certain situations. Sometimes a fault doesn't actually lead to a failure. Sometimes a fault doesn't lead to an observable difference. In other words, a fault may occur, but you may not see that fault exhibited in the output you receive. It may be something that's just internal. So we have errors, faults, and failures. And then if we think about what a defect is, well, a defect is usually just defined as being a fault or a failure. So, some people equate defects as just faults, some equate them as just as failures. I typically think of a defect as being a fault or plus failures. So all the faults and failures would be considered defects. Does that make sense? Great. So far, I've only been giving you definitions. I haven't given you any metrics. And you might say, okay, I thought this was a lecture about metrics. So now we're going to get more into product metrics, right? So let's talk about a metric that is very important to defects, which is called defect density. And remember we talked about reliability back before I kind of went on this tangent of definitions? Well, reliability, a metric for reliability is defect density. Because remember, reliability is an attribute of a software system, of the software product. And it's the metric we use to measure that attribute is defect density, is one of the metrics we can use, I guess I should say. So defect density can be thought of as the number of defects that are found divided by the system size. Does everyone agree with that definition? Okay. So everybody's saying makes sense. Okay, great. So remember, I'm saying here system size. And size normally, when we're measuring size of the software system, we're normally measuring it in terms of the lines of code. KLOC or LOC KLOC is 1,000 lines of code. LOC is lines of code. So typically, we're often talking about units of defect density or number of defects per 1,000 lines of source code. Okay? And this is widely used. Yes, exactly. Or K, as not kilos, as K as in 1,000. So what we're looking at here is thousands of lines. And so this is widely used as an indicator of software quality, defect density. High defect density, poor quality. Low defect density, high quality. Okay, but does this make sense? How many of you would agree this makes sense? I'm going to just pause and do a little poll. Hey everyone, we're back. So I just ended the poll. So remember, what I am asking really is defect density a good indicator of software quality? And in order to answer this question, you need to know what defect density is measuring. And I've tried my best to explain it to you here by giving you the definition of defects based on faults and failures, and what reliability means. So I've tried to give you a good background to answer this question honestly and with an informed opinion. So the question I asked was, is defect density a good measure of software quality? And a number of people didn't respond, but there are 34 of you did respond. I appreciate that. Had 8 votes for yes, it is. 10 votes for no, it's not. 14 votes for maybe. And 2 people said, what's quality again? So in general, people were very skeptical. And I think maybe they think I only do a poll whenever I want to give a trick question. So anyway, let's go ahead and answer this. I'm not going to tell you the answer. But what I will do is I will just comment on it, or I guess I will mention a few of the comments that are in here. Not all defects are created equal, so it depends on the defects. Someone said it is a standard reliability metric. That suggests it's good, but the fact that you're asking suggests it's not always so good. So this is like one of those mind tricks that I think somebody thought I was doing. Someone said that they don't like it because it's the number of defects found. They think it should be the number of defects divided by system size would be a measure of quality. So if the defects, if you have a poor method of finding defects, then that's going to make this number not look as good. And then someone asked about more compact programming languages. So if a language is more verbose, requires more lines to write the same program, does that mean it's going to actually is it going to actually be it may be better or worse simply because it has less or more lines? And someone else said mind games. So I'll take it as there's a lack of trust in my in what I've put up here, but that's okay. I wanted to get you to think, and if you've thought a little bit about this, I'm very happy. So let's think about this a little bit. In order for this to be a good measure, if let's say, is this a good indicator of software quality, or is this a good indicator of software reliability? Maybe if we narrow the definition down to just reliability, people would feel more comfortable. Well, here's something to think about, right? What is it that really impacts reliability? Is it defects, faults, failures, what? Failures, right? If we go back and look at that definition of reliability I gave you, it's the probability that a system will execute without failure in a given environment over a given period of time. We also looked at the definition of faults and failures as being a fault is when a mistake happens in the software. A failure is when the program when the program is run in certain situations that's observable by the user. And a defect is often a combination of these. So out of the defects, faults versus failures. Failures are much more crucial to reliability than faults. Agreed? Agreed? Failures are more important to reliability than faults? Okay. So, now this is, I'm going to warn you, this is slightly from a little bit of an older data set. I don't have a newer data point to look at. It's one of those things that's tough to find data, but I do want to point it out, and I think it's good from a understanding perspective. But I would encourage you, like any data or any empirical point, it's always useful to go and look at, because this, I'm putting this on YouTube, so this could be here 10 years from now. So if somebody is looking at it, check out the latest results and make sure that the data still backs up the statements that are made whenever you see something that's empirical. Okay? So here's an example here of the relationship between faults and failures. And this actually comes from something like a long time ago, right? This is like 40 years ago originally. But the point is that if you look at this, faults are not always a good predictor of failures and vice versa. And more recently, it was found in a study that 35% of faults caused about 1% of failures, and 35% of failures were caused by only about 2% of faults. So if most of the faults are caused by only a few, if most of the failures are caused by only a few faults, measuring the defect density isn't necessarily going to tell you how reliable the software is, right? Because you need to, it's really, the question comes down to these little orange one here. If you have a lot of these, then it's gonna matter. But if you happen to have a lot of the faults that are not the ones causing failures, it may not be as reflective. So someone said faults should have a weighting based on how many failures they produce. Sure, except here's the challenge, right? With failures, remember what I said about failures, and we're going to go back. I'm going to go back again. When we were talking about this, there's a couple things I said about reliability. I said that no single number for a given program, right? It depends on how the program is used and its environment. So one of the big challenges here is figuring out things like the failures, because you really need to have a good knowledge of all the different types of environments, all the different types of ways it's utilized, or you need to at least have a good model of that or a good sample of that, depending on how you're trying to calculate this. So it's tricky to do that, okay? But this is a little concerning that there's a small number of faults that are causing the majority of the failures. Okay. So this is an aside, and I just want to mention this as an aside because I think it's related to this, but it's about process. Okay. So there's also the effectiveness. So there's what we were just looking at was defect density, right? And you can use defect density to use as a measure for reliability, like people have been doing. And this is what we were just exploring. Is this a good measure? But you can also measure defects and defect rates as a way to understand the effectiveness of defect detection and defect removal. So the number of defects found per hour. So this is slightly different, right? This is defects found per hour, not number of defects per 1,000 lines of code. So it's not the defect density, it's the rate that defects are found. This is often used as a software process metric so that we can understand and evaluate different types of testing. And in fact, it's also been used as a way to compare the effectiveness of inspection versus testing. And I just want to point out here, this is one of those things that's interesting. because defects found per hour. So inspections, you might be able to find more defects, in the case of this data point. But what you really also want to be looking at, so there's defects found per hour. It's also useful to look at and understand how many new defects or defects not found in other techniques does a particular technique find is also useful. So I just want to point out as an aside here that we do actually use metrics involving defects in the process to evaluate process as well, and activities in process, not to just evaluate our product. Okay, so that was a little bit more about external product metric, right? Defect density, which is looking at how many failures are happening as the software is being executed per 1,000 lines of code in the environment. Now, the other group of product metrics that we're interested in here are internal product metrics. And internal product metrics, these are ones that are actually measuring the software code, the design, the functionality, and so on. And different organizations may have their own. For example, in the U.S. military, they have hundreds of these that they actually do for source code. And a lot of these measures are easy to automate, but the challenge here is that it's like I'm a big believer in metrics, measurement metrics, and the value that metrics can have in improving, in getting you to better understand what you're doing in your software process and your software product and improve upon that. However, I also believe it's really, you want to be measuring things that you understand, right? And so having a lot of metrics that you're not really sure how you're using or what they mean isn't necessarily always good. So it's always important to remember that when you have a different metric, you should be looking at what attribute is of the program is this categorizing, or characterizing, I should say, in the case of product metrics, internal. So let's look at software size. This is something we touched on last lecture in some of the examples, but we didn't spend a lot of time on it. So software size is something we talked about. And I even mentioned it, we talked about defect density, because defect density was an indirect measure, right? Well, it wasn't indirect per se, but it was in that we had to know the number of lines of code in the system to calculate it. So it is an indirect, so it's the lines of code and the number of failures or defects. So a software size, I told you, could be measured by counting the total number of lines of code, or often it's written in terms of thousands of lines of code. And it can be used, as I mentioned, as an indirect measure for things like productivity, effort and cost estimations, quality assessment estimations, such as the defects per lines of code. And there are other alternatives to using lines of code. There's something called KDSI. Have you ever heard of that? Those are thousands of delivered source instructions. So delivered source instructions will exclude commented code. It'll also exclude instructions. So this is really talking about source instructions delivered. So it's including code that may be utilized for debugging purposes, but not part of the final product, etc. And then there's number of non-comment lines of code is another one, where you strip out the comments and you look at that. Source instructions are interesting because they also, going back to KDSI, they also don't factor in, as I mentioned last time, this idea that you could have, for example, one instruction that spans multiple lines, or could be on a single line, depending on how you indent, how you wrap, and so on. So by looking at source instructions, you remove the formatting aspects from the measure of size. So how the programmer has formatted their code doesn't actually impact the measurement there. And lastly, you could actually look at it as number of characters of source, or bytes of object code, right? Or number of machine instructions, or there's a whole bunch of things you could do if you want it. So these are all things you could actually look at. Now, here's an example. This is a Toshiba productivity. And this is an older example, but I like it because it's interesting. So this was when, back a long time ago, they introduced their first software workbench system. And If you want to know what is the software workbench system, think about this in the context of um, uh, maybe the software workbench. Think of it as like an early IDE sort of tool or something like that. It's a CAD tool. It's like one that's used to aid developers. Okay, so if you look at it here, instructions per programmer month. What do you notice? What has happened? It goes up pretty linearly. So it seems to be fairly flat. And then when this is introduced, it actually starts to go up. So what does that mean? Is that good or bad? It's good. So it means what? More instructions produced per programmer. It means increased productivity. Yeah, there's a good, someone had a good comment. Depends on how efficient the extra code is, depends on the quality of the code. That's not indicated here. So this is something that's the kind of question you should ask. And I'm glad to see people asking it. But it's something just to think about, right? No one even asked me what language they were using or anything like that. But anyway, let's move on here. I'll talk about this in a bit. So let's look at the issue of lines of code here. Why is lines of code? Actually, you know what? We're going to just pause for a minute. I'm going to go back to this. What I want you to each do is actually look at this, and I'm going to give you another poll, and I want you to tell me if you think this is good or bad. Okay, we're going to actually do a little poll here about this. So, as I was just mentioning after our discussion, we did a little breakout. We ended up doing a bit of a breakout. In general, the software workbench system was something that was used at Toshiba, and as far as I understand, actually was successful. So there's a presentation, I think, at ICSI 84, which is the International Conference on Software Engineering, where they discussed, representatives from Toshiba actually presented and discussed the software workbench system as well as the hardware workbench system, and how they actually were able to benefit the software they produced as well as their developers, and sort of some lessons learned from this experience. So I just also wanted to mention here, because we had that last poll and I think everybody was sort of like, oh, well, if he's asking, there must be something wrong with this. So sometimes it can actually be a good thing. Oh, where did my slides go? That was weird. Okay. So just wanted to mention that there a little bit. And then we talked about, the last thing I wanted to do was mention to you, because I haven't discussed this as well, but lines of code as a measurement, as an attribute. What's the issues with lines of code? Well, one thing with lines of code versus using it as a measure for the size of the software system, and I mentioned this last time, is that lines of code is really more of a measure of length, which is a physical characteristic, not size, which can be thought of as a logical characteristic of the software system. And you just need to understand what it is you're measuring in that here. So challenges with lines of code, one of the things is that people who don't understand that it's a measure of length, not size, really, that means that they actually use it as a surrogate when they want to say that the functionality. They'll say, well, this software has more functionality than this one because it's bigger, meaning it has more lines of code. Or this software is more complex because it's bigger, right? Or this is going to take longer to write because this is 1 million lines of code. This thing is 800,000 lines of code. It's going to be less effort. Not understanding that 800,000 lines of code might be way more optimized might, there could be a whole host of reasons why it's less. So when you have people using it as a surrogate for these other things, you run into problems. So that's something where, you have to always be careful about understanding what attribute a metric is measuring or is characterizing. Another thing here is that lines of code don't actually take into account some of the things like redundancy and reuse. Okay? One example of this is in like banking software, and this was an example from Jim Cordy, where he was mentioning that there was a banking software that they worked with, I believe it was, where or there could, where there's 500 million lines of code and only 100 million lines was unique. And part of that was there's always an emphasis on reuse of code because code that already exists has been tested and trusted. So therefore, if you reuse it and modify it instead of writing new code from scratch, it would always be a safer choice. Again, lines of code. The other issue about it is because it's length of a program written in a particular language, you can't compare and say anything about the size of a program written in Java, as somebody just mentioned, and one written in COBOL. You can't, it's comparing apples and oranges, as the expression goes. The other challenge with lines of code is how big, if you want to know how big the software is, you can't use lines of code until it's written, right? You have no way of using, like when you're doing requirements, to know how big the software will be if you use LOC as your measure. If you're doing design, you have no way of knowing, right? It's only after the software is completely written do you have the length of the software. So therefore, you don't know it very early on in development. Here's some other alternatives or some other size measures. One of them is length, which we can think of as the physical size. This is what LOC does. Functionality is something that we can also measure. So for example, with functionality, we could be interested in measuring how many functions a particular software system has, so how many features, that kind of thing. Complexity. So there's different measures of complexity. Have you guys heard of complexity? Well, one thing we could think about is problem complexity, which is how complex is the problem that the software solution is trying to solve. We could also look at the algorithmic complexity, right? How complex or efficient the solution is. You've probably talked about algorithmic complexity in your algorithms course, right? Yeah. Structural complexity, measuring the structure of the program used to implement it, right? And cognitive complexity is how the effort required to not program it, but to actually understand it. So how hard is it to understand, basically, is what cognitive complexity is. And this takes us to the last thing I want to discuss today, which is the notion of code complexity. And code complexity is something that's really important to look at. And there are different measures of code complexity, but it's trying to sort of measure cognitive complexity a little, but by looking at the complexity of the source code. And the idea is that it's looking at, or it's trying to characterize it based on things like how many decision statements, how much nesting there is of loops and blocks, and how long methods and classes are, right? The idea being that something that has a higher density of if statements, more depth in the terms of nesting of loops and blocks, and a longer length is more complex than something that doesn't have those things. And some of the measures we learned about are like cyclomatic complexity, software science, and so on. I'll briefly mention the Halstead one because I think it's interesting, but in the end, I don't think it's something that I'd recommend. I would recommend using the cyclomatic complexity. And Halstead's metric is basically this idea that the source code, if you think of your source code as a sequence of tokens, right? Each token has operators, and operands, right? So operators are things like plus, minus, division. Could also be things like, you could have other operators as well. Things like swap for swapping two numbers, something like that. And operands are the symbols that you have that are involved in these expressions. Okay? So like if you had x equals a plus b, you've got operands there, or would be things like x, a, and b are operands. And Halstead's metric looks at the length and the vocabulary of a program. So the length is looking at the total number of operators, this includes duplicates, and the total number of operands. That's the length. The vocabulary of the program is the number of unique operators and unique operands that are used. Okay? This is very different than counting lines of number, or lines of code, right? And then what you could do in this Halstead Software Science metric is you could then use these things in a number of formulas that he came up with, which would allow you to provide estimates of things, including the effort that it would require to create this program with this size, that kind of thing, or the time required to create the program. Or you could even use, he had an estimate which would allow you to use, if you wanted to know the length of the program, if you knew how many variables, operators, and operands you were using, you could then calculate the total length of the program, which is theory one, using the number of operators and operands that will be in the program. So this is all interesting. I find it's not as useful because in the end you still have to know how many operators and operands are going to be in your program, which often you don't know till you write the code. So to me, this is interesting, but I usually just put it in here for just something, insight, so you can see some of the different perspectives that have been come up with over the years. The one that's a little more, I think, practical is to look at cyclomatic complexity. And cyclomatic complexity is something that's really useful for something we've already done, which is we've already talked about path coverage in testing. Well, it turns out that in cyclomatic complexity, cyclomatic complexity is measured as the number of linear and independent paths in a graph or in a program. Well, guess what? Number of linear independent paths, that is exactly what we're looking at when we do path coverage. So if we drew the diagram like we see here and trace through all the independent paths, meaning each path that includes at least one statement, or one, in this case, node that wasn't in another path, is unique, we'll actually get the same thing as what's calculated by looking at using the cyclomatic complexity. And as we can see here in this diagram, we could calculate this as being the number of edges. If we know the number of edges and number of nodes, it's number of edges minus nodes plus 2. And that gives us 5. Okay? That is the number of unique linearly independent paths. That's the complexity. So a piece of code with more paths through it, more linearly independent paths, is more complex than one with less linearly independent paths through it. Now, the nice thing about this is that you don't have to know all the nodes and edges to calculate this. If you look in this diagram, there are actually 3 decision statements in it, right? Each diamond is a decision statement. And it turns out you can also calculate cyclomatic complexity simply by looking at the number of decision nodes. So if you know how many decision nodes there are, you can take that number, 4, you can add 1 to it, and it will give you the number of unique paths. Now, this is actually really great for path coverage testing, because if I ask you, although we don't have a final in this course, but if I did ask you on a final, how many, does a set of tests provide path coverage? for this piece of code, if it only had 4 tests, you could immediately say, no, it doesn't, because you know there's 5 paths, so there has to be 5 tests. So this is something that you can use to help you when you're doing this type of testing. From the perspective of complexity, just knowing this number 5 doesn't mean anything, right? Like we have to have an understanding of, well, is 5 a good number or a bad number? And McCabe, when he proposed this, he proposed that modules, meaning functions or methods, should have less than 10 complexity. Is that good? It sort of depends. I would argue that it sort of depends on how dense the code is as well, in terms of because the thing that this does is it looks at the complexity of the code but ignores the complexity of the statement, if you understand what I mean. So it doesn't factor in that some statements can take a lot more to understand than others. So if you're dealing with, say, for example, scientific code, I would argue you want to have a lower cyclomatic complexity than if you're dealing with a web app code. Just as an example. Okay. So then the last thing I want to say regarding this is that just that McCabe's complexity or cyclomatic complexity, this is just one of the many flow graph based complexity metrics, and there are advantages to different ones. The thing I like about some of these is when they're independent of the actual programming language, which many of these are. And the nice thing about the ones that I've listed here, some of the other ones like maximum path length, number of interactions, number of alternate paths, and etc., is they're pretty much, if you can compute the flow graph, you can automatically compute the metric. And so I just want to mention this here to you. And I'm going to only talk about product metrics today. So that's what we were talking about. I have included at the end of the slides more information about process and project metrics. I'd encourage you to read those on your own, but I did want to go through the product metrics today just to give you some insight. So just in summary here, what have we learned over the last 2 classes? We've talked about measurement being characterized by attributes of entities. We talked about them being direct or indirect. They can be used for assessment and prediction. And then we also did a framework for these metrics. And then we also talked about product metrics today, including external metrics such as defect and defect density, and internal metrics such as size and complexity. And I hope I know it can be a little dry since I was talking about metrics, but I hope I've made you think a little bit about some of these metrics and what they mean and why, whether or not they're useful. My point is not to critique or criticize the majority of the metrics. I've just picked a few that I wanted you to think about, because I think you never want to go into doing software metrics blindly. You never want to just use the metrics and not actually understand or contemplate what they're measuring. So if you go into metrics not with a skeptical mind, but with the mind of understanding and fully grasping what you're trying to do, you'll be fine when it comes to using software metrics. So that's sort of my last thing I want to say. Yeah, I'll stick around for a few minutes if you have any questions. Thanks.